In this video, we're going to talk about the Larmor formula. The Larmor formula describes how power is radiated by accelerating an electric charge. The Larmor formula is important to understand because other than atomic processes, accelerating charges is how almost all radiation is produced. So the key word here is that we need to have an accelerated charge. So let's put down an electron with an electric field drawn in blue here. Now, because an electron has a negative charge, this electric field happens to point towards the electron. And in general, the force that we measure as a result of this electric field is given by the product of a charge with an electric field, plus another component that we're not really going to worry about right now, which is the cross product of the velocity of a charge with the associated magnetic field. Now, if we assume a static charge, so it's just sitting there, it's not moving at all, this electric field extends off nearly infinitely in all directions. And you'll notice that the electric field always points in the radial direction. So it's always pointing back in the radial direction towards the electron at the center of it. And without any B field, that's also the direction that the force will point. So if we write that down, that's the E field has a radial component that points in the r hat direction with a magnitude E that depends on how far in radius we go. And if it's a static electric field, we have no oscillations. But we know that Maxwell's equations do support oscillations. In a previous lecture, we showed that plane waves, which are photons, they carry radiation, they travel in a direction k hat associated with the direction the plane wave is propagating. And we know that the E field has to be perpendicular to that direction, as does the B field. And in fact, the E field and B fields are themselves perpendicular. And we also showed in a previous lecture that we can describe any radiation as a sum of plane waves. So what we found is a general property of light, which is that for whatever direction that light is traveling, the E field and B fields associated with that light need to be perpendicular to that direction and perpendicular to each other. Now, if we somehow got this electron to produce a photon, a disturbance in the electromagnetic field, it would have to travel in the radial direction. Any photon it produces will leave the electron. That means that the k direction that our plane waves are traveling is going to be in the radial direction. And so, with an electric field that points in the radial direction, we know that the electric field that we're seeing is not associated with any oscillation. And in fact, we knew this because it was a static electric field. Nothing is changing. But now let's consider if we had a moving charge, a charge moving at a constant velocity. So suppose we have, again, our electron here in the center, but now it's moving at velocity v. Now, because this electron is moving at some velocity, we know that there actually must be a B field associated with this electron, but we're not going to consider that B field right now. We know that the B field arises because of relativistic effects, that since this electron is moving with respect to our frame of reference, the length contraction and time dilation associated with Lorentz transformations mean that there's another component of our electromagnetic field, the B field, that affects charges in motion. But we're just going to continue to look at the E field. It's important to note that the electric field of this electron is still radial. If we're sitting out here at this black point here with a charge, and this electron comes by us moving at constant velocity v, then at some point that electron makes its closest approach to us. And as it does so, its electric field will point strictly in the up-down direction for us, and we may feel an attraction of our positive charge over here towards that electron. But we'll only feel that attraction some amount of time later because this electron moved by, and it took some amount of time for the field from that electron to get up to us so that we can feel it, because that electric field can only carry information at the speed of light. But the fact is, the electric field will still point straight up and down, and the information from that electric field was propagating radially outward from that electron. And so the E field and the direction of propagation are still parallel to one another. So even though this seems like a more dynamic situation with an electron actually moving, if it's moving at a constant velocity, the E field is still radial, and there is no disturbance in it. So there is no oscillation, and hence no plane wave. There is no radiation from a charge moving at a constant velocity. And in fact, we knew this kind of had to be the case just from special relativity. Special relativity tells us that there is no absolute reference frame. And so whether or not an electron is moving in our reference frame or not shouldn't affect whether or not radiation is produced. Otherwise, that radiation could be used to deduce an absolute reference frame. And in fact, this is what they were trying to do towards the end of the 19th century when they hypothesized that there was an ether that carried the electric force. And the Michelson-Morley experiment showed that there wasn't an ether, because if there had been, we would have been able to detect disturbances in the electric field for motion relative to the reference frame of the ether. Just like if you were swimming in a pool, your motion relative to the water could be detected by the waves that get produced. So how do we get radiation out of a charge? Well, we know we cannot be in an inertial reference frame, so we must have an acceleration. So let's create an acceleration. Let's suppose that initially we have a charge centered on the x here, which hasn't been moving ever. So it has an electric field that radiates off infinitely in all directions. And then at time t equals 0, we have an instantaneous acceleration. And we'll call this instantaneous acceleration A, which produces a change in velocity, delta v, in a very short amount of time, delta t. So with this new velocity, delta v, at some time later, much longer than delta t, but at time t later, we'll observe that the electron has moved from its initial position over here at the x over to a new position over here. And the distance it will have moved is delta v times t. So if I redraw this picture over to the right, what we'll see is that far out, the electric field is still centered on the original location of the electron because there hasn't been enough time for information about the acceleration of the electron to reach there. So far away, we have an electric field that looks just like it always did. And then internally, close to the electron, we have a new electric field that reflects its new velocity with this electric field translating along with that electron. So internally, we still have a radially oriented electric field for an electron moving at a constant velocity, but this electric field is centered on the current position of the electron, which has been moving at speed delta v for time t. Now we have something interesting because we have two different electric fields, but we know electric field lines are conserved in regions where there are no charge. And we also know just by continuity that we must have that as this electron transitioned from being stationed at one location to moving at a constant velocity, that we needed to have some transition from where the field lines used to be over to where the field lines are now. And so in fact, we need to connect up these electric field lines, which I've done here with the red color. But in directions perpendicular to that acceleration, we see that there's actually a sizable jog between where the electric field used to be and where it is now. And this jog occurs over a relatively thin shell here. And we can calculate the width of that shell and the radius of that shell. The radius of the shell, which I've written down here and circled in green, is given by the amount of distance that this disturbance in the electric field can have traveled, knowing that it must be traveling at the speed of light. So the radius of this shell, r, is given by ct, the product of the speed of light times the amount of time since the disturbance happened. Now the thickness of this shell here reflects the distance that light traveled over the course of the acceleration as it happened. So if the acceleration happened over a time interval delta t, then the width of this shell is c times delta t, because this is the only interval of time over which we were not in an inertial frame. So now let's look at this disturbance. This disturbance, as we said, is propagating outward radially from the old location of the electron at the speed of light. So now we have something that is moving in the radial direction, r hat, at speed c. And we can also see that within this shell, the electric field is not perfectly parallel to that radial direction. It has a slope here, which means that some component of this electric field must be perpendicular to the radial direction. So we have a disturbance in the electric field, it's propagating outward, and we have a component of the E field that's perpendicular to the direction of the propagation. Now we haven't looked at the B field, because that's not really part of this derivation, but the B field actually shows similar properties. The B field will be perpendicular to the E field, and it will be perpendicular to the radial direction. So now we have all the criteria for a propagating oscillation according to Maxwell's equations. What we have is locally a plane wave moving outward. And I can alternately call this plane wave radiation. I can call it a disturbance in the electromagnetic field. I can call it a photon. So I'm beginning to strain my abilities as an artist here. So what I'm interjecting here is a simulation in 2 dimensions of what happens when you accelerate a charge. And what we have originally at the center location is the charged particle with an electric field that is uniform radiating outward. And then shortly into the simulation, this charge is given a small kick that gets it moving to the right-hand side, moving at constant velocity v. So as long as it's moving at that constant velocity, as you can see kind of locally to this charge, field lines remain radially oriented, moving along with the charge. But as we were discussing before, there's a thin shell of a disturbance in the electric field over which the field lines must reconnect. And that disturbance radiates outward at the speed of light, away from the original location of the charge, even though the charge inside of that shell has meanwhile been moving off to the right. And you can also see that the magnitude of the jog, the amount of discontinuity in the electric field, is much greater in the perpendicular direction than in the parallel direction, which is to say that moving up out of the page here, you can see a large discontinuity which reflects the full acceleration of the charged particle off to the right. But in the left and right direction, there's only a small discontinuity in the electric field because relative to those directions, the position and velocity of the electric field has not been disturbed as much. So now let's see if we can figure out how much power is being carried outward in that shell resulting from the acceleration of this charge. And to do that, let's zoom in on one area of our shell here. So this x again is the original position of our electron, and then over here at a distance delta v times t is the current position of our electron at time t. Originally, if we just examine the electric field propagating outward at some direction theta from the x-axis here, the original electric field will have continued off infinitely in that direction. But now at some time t later, inside of this shell, we'll see that the electric field propagating in that direction theta will have gotten up to this point on the inside of the shell, moving along with the electron. And so over this shell, we have to have some reconnection, which I've drawn in orange here, between the current electric field that's tied to that moving charge, connecting up to the electric field of the stationary charge at position x here. And this disturbance, as we've seen, is moving outward radially in the r hat direction. So what we'd like to do here is figure out how much of this electric field here is parallel to that r hat direction and how much is perpendicular to it here, which I've drawn with a little perpendicular off here. Because the component in the r hat direction is not part of the plane wave that is propagating outward. It's part of the quiescent electric field. But the part that's perpendicular, this perpendicular component of the electric field here, is propagating as part of this oscillation. It's part of the radiation emitted by this charge. So we need to figure out what is the E perpendicular component of the electric field here. So to do this, let's look at the slope of the electric field here in orange. We know the slope is given by 2 components. There's the component in the perpendicular direction to r hat, and there's the component in the radial direction, r. And we need to figure out the slope of that line. Well, just geometrically, we can work out what this slope is, because we can see that in one direction here, the distance is c delta t. That's the distance that light could travel over the interval of acceleration here. So what we really need to figure out is the component that is perpendicular to that, which results from the distance that this charge has moved since the acceleration has taken place. Now, because this acceleration produced a velocity change delta v, then the change in position of this electron sometime t later is just delta v times t. So that's the new position of this charge as a function of t. And you can see that the perpendicular component of the electric field here is related to that distance that the charge has traveled. And in fact, if you work out the geometry of it, this is just delta v times t times the sine of the angle theta that we're examining here. Easy way to check that is if theta is 0, there is no discontinuity, just like sine of 0 goes to 0, and it's maximal when theta is 90 degrees. So now we can write the slope of our line here as the distance in the perpendicular direction, which as we said is delta v times t times sine theta, divided by the distance in the radial direction, which is c delta t. So now we can do some cute algebra. The first thing that we can do is, as I've circled in orange here, is we can group the delta v and delta t together, noting that delta v over delta t is actually the original acceleration of the electron here. We can replace delta v over delta t with a, the acceleration. We now have a much more generic form here for any acceleration. And the second cute little piece of algebra we can do is, instead of having time t here, which is a kind of ad hoc amount of time later, we can express that instead as a function of the radius and the speed of light that we're looking at here. As I've circled in green, the radius was given by the speed of light times t, and therefore we could substitute instead of t the radius divided by the speed of light. And when we do that, we get an expression for the slope of the electric field here as the acceleration times the radius divided by the speed of light squared times the sine of the angle. So now we've solved for the slope, but we don't actually care about the slope. What we care about is E perpendicular. That's the magnitude of the electric field that's associated with this plane wave. It's associated with the radiation propagating outward. So if we can plug in for what the radial component of the electric field is, we can solve for the perpendicular component. Now we know how to solve for the radial component of a quiescent electric field. That's just given by the charge divided by the radius squared. And instead of plugging in the charge of our electron, I've substituted in Q so that we could do this for any charge. So given this radial component of the electric field, we can now multiply this against the slope that we already solved for and solve for the perpendicular component of the electric field. And here we have it. The perpendicular component is equal to the charge times the acceleration times the sine of theta over c squared times r. So we're almost there now. We have the perpendicular component of the electric field, but we don't actually have the power that's being carried. Now, as part of our derivation of plane waves, we ended up solving for the energy density associated with the electric and magnetic fields. And if you recall, we knew that electric fields had to be storing energy because when we take the plates of a capacitor that's built up a charge on them and therefore attract each other and pull them apart, we have to do work to do that. So we're injecting energy into the system, but at the end of the day, nothing's moving. So we had to have stored that energy somewhere. And we deduced that we were storing the energy in the electric field itself. And we derived what the energy density of that electric field was. It was given by E squared over 8 pi. And similarly, if we had energy stored in the magnetic field, it was given by B squared over 8 pi. You recall this energy density was energy per volume. And I'm going to take one little shortcut here, which is that because we know we have a plane wave oscillation that we're setting up locally here, and we know that for plane waves, the magnitude of the E field and the magnitude of the B field must be the same. We say that B squared is equal to E squared, we can get the total energy density for an electromagnetic wave as E squared over 4 pi for a plane wave. So what we can do now is, knowing the energy density associated with the electric and magnetic fields of a plane wave, and knowing the magnitude of that electric field and the volume that encloses this disturbance in the electric field, we can calculate the total energy associated with this disturbance. So U is equal to E perpendicular squared over 4 pi. And so the total energy, E, is equal to the volume times that energy density, which is this times the volume of this shell. And for a thin shell, we can call that volume the surface area of the shell, which is 4 pi r squared, times the width of that shell, which was c delta t. So this energy, which I want to be careful not to confuse with the electric field, this energy, E, is E perpendicular squared averaged over this whole shell. So if I'm going to plug in my formula for E perpendicular squared becomes Q squared A squared over C to the fourth R squared times the average of sine squared theta over a shell, which is 1 over 4 pi times the integral sine squared theta d omega, where omega is a solid angle. So that's the E squared component, and then this whole thing is multiplied by the rest of what we had up here, which was 1 over 4 pi, and that's the 4 pi associated with the energy density here, times the width of the shell, which was 4 pi r squared c delta t. So now algebraically, some cute things are going to happen. First of all, this r squared over here cancels with the r squared that is the surface area of our sphere. So the energy in this shell does not depend on the radius of this shell. And of course our 4 pi's cancel out over here, and our c cancels out one of our c to the fourths over here. So the only tricky part left is really what is the integral of sine squared theta over a sphere. And rather than getting caught up in the calculus of doing this, which actually isn't too hard, you can do it for yourself, or you can work it out numerically, this integral comes out to be 8 pi over 3. So the energy in this shell is given by q squared a squared over c cubed, and our 4 pi cancels with our 8 pi to give us 2/3, and we get a 2 over 3 times delta t. So this is looking pretty good, but this delta t is a little ugly. But what you can do is you can divide this delta t over here, and you can say the energy carried over a time interval delta t. Well, the change in energy with time, that's just the power carried. So that's this power, P, is given by, just to simplify things here, 2/3 q squared a squared over c cubed. And this right here, this is the Larmor formula. And this is a very generic formula. It just says that the power carried off in the electromagnetic field as radiation that results from accelerating a charge is 2/3 q squared a squared over c cubed. And this is the total power. Now, there are just a couple things to remember about the Larmor formula. What we have here is an expression for the total power carried off. But we need to remember that because of this sine angle component up here, that not all directions receive the same amount of that power. That in fact, a lot more power is radiated perpendicular to the direction of the acceleration than is received in the direction parallel to it. So if you drew a picture of an electron being accelerated in this direction, the amount of power received as a function of direction is much greater in the directions perpendicular than parallel. And if we did this in 3 dimensions, this would be a full donut, where the axis of that torus points along the direction of the acceleration, but the amount of power received is maximized in all of the directions perpendicular to that. So that's the first thing to remember about the Larmor formula, is that power is not isotropic. And the second thing to remember is that we've said nothing about the frequency of this plane wave. So we did not mention omega, the spectral frequency. And this is because the spectrum of the emission that results from accelerating a charge depends a lot about the time variation of the acceleration. So we could figure out where the radiation goes, but through this whole problem, because we've abstracted the whole acceleration as A, we have nothing that allows us to solve for what the spectrum of the radiation was. So we do not know how much energy is in each photon. But we do know that whatever the energy per photon is, that times the total number of photons emitted per second will add up to this total power given by the Larmor formula. And that's the Larmor formula. Thanks for listening.